So today we're going to talk about what it means to simplify fully. First of all, what we want to know is that that means something specific. There's sort of two things that we want to be aware of, that when it says simplify fully, that this is what it's talking about. And one of them is fully factored. And the other is one single fraction. And we'll look at some examples of sort of both different types of simplifying. And after we've done one or two, we'll talk about why you might want to do this. So you can think about that maybe. Does that make sense? Everybody got it? So again, this is like just a test question. Down the road of this course, you'll know when you have to do this and when you don't. But on a test, some of the questions will say first line only, tidy up the monomials kind of thing. And then there'll be a separate question that says simplify fully. And this is what it means, what we're starting today. All right, so let's take a look at this first example. Nothing I can do to simplify or tidy up before, so we're just going to go ahead and take the derivative, which you can start. Don't let me do it. It's always good, a little bit of extra practice. Derivative of the first times the second plus the derivative of the second times the first. And each of these are power of a function, right? So when I take the derivative of the first part, it's going to be 5 times 2x plus 1, subtract 1 from the exponent, and then times the derivative of what's inside. And I would imagine many of you are starting to look ahead and do that together. So like, I know that I'm going to take the derivative of what's inside eventually anyway. I can just multiply it by 5 and start with 10. You don't have to do those in separate steps. Those of you that can look ahead, and I will start probably today doing that as well a little bit, shortening up the process. Plus the derivative of the second part. So bring the exponent down, 3x plus 2. Subtract 1 from the exponent, times the derivative of what's inside the brackets, which in this case is just 3, times the first part. So this is what we've already done. That's what it would look like if it was first line only. So what can I do to continue here? Anybody have any ideas? Is it fully factored? What do you think?
We can expand and simplify factors to out or something.
Yes. Expanding and simplifying would be tricky with these exponents. Sometimes you might be able to do that.
We factor it 3x plus 2, and factor it by grouping.
Yeah, it's actually just common factoring, but I think you're noticing it correctly. Isn't there a common factor of 3x plus 2 in both of these terms? You can think of these as two separate terms. So all we're doing now is common factoring. I've got term 1 and term 2. And they actually have more than just 3x plus 2. They each have a 2 in them at the beginning. They each have some 2x plus 1s, and they each have some 3x plus 2s. So that's exactly what we're going to do. We're going to common factor. So I pull out the 2. How many 2x plus 1s can I factor out? Well, I've got 4 of them here and 5 of them here. So I can pull out 4. Does that make sense? And how many 3x plus 2s? I've got 4 here and 3 here, so I can pull out 3. And then we got to be able to figure out what's left. 10 divided by 2 is going to give me 5. 2x plus 1 to the 4, I factored all of them out, so I've got none of those. 3x plus 2 to the 4, I only took out 3, so I've got 1 left. 12 divided by 2 is 6, and same thing in this. And there are some patterns here that these things kind of tends to work out similarly every time. So once you've practiced this a little bit, you'll start to get used to these things. It's where you want to get yourself to. I started with 3 of these, and I took all of them out, so I'm done with those. I had 5 of this bracket, and I only took out 4, so that's the one that I have left. So this is kind of what I mean. Like, often we notice that it's going to be a number or maybe a monomial times one of the brackets, and then something times the other bracket type thing, right? Like, that'll happen fairly often. What now, do you think? Expand and simplify in here and see what happens, because that part's not fully factored. This is all fully factored, but this part isn't. It's a disaster. So what's this? 27x plus 16. And that could be factorable in some situations. So one of the examples we're going to do, you're going to see, like, part of the tricky stuff of this is don't be too quick to move on to the next question. Really get in the habit of looking at every little part. Is it factorable? All the different factoring skills that you have, remember all of them. We'll see some different examples of the different kinds of things that you might come across in some of our examples today. But I think that one's done. Any questions? So that's a typical one when you that you have to simplify it fully, you just have to do some factoring and regrouping things, that kind of stuff. Okay? Any questions? So this one's already written out for us, ready to be factored. Again, no extra work to do. So you can go ahead and try this one if you want. The derivative of the first bracket in this case is 2x times the second bracket. Plus the derivative of the second part. So that's going to be 1/2 times x squared plus 2 to the negative 1/2 times the derivative of what's inside, and then all of that times the first bracket. I'm going to clean this up a little bit. So this is 2x times the square root of x squared plus 2. Again, we often rewrite these back in radical form. I notice that I've got a 2 and a 2. So I can divide those out, looking for different things like that happening. So this ends up being plus x times x squared plus 4 all over, because this is a negative exponent, so it's going into the denominator. And again, it's an exponent of 1/2, so it's the square root of all that. Any questions on that one so far? So what was the other rule when we said simplify fully? One fraction. And so if I've got two separate things, I've got to put them together. How am I going to do that? How do we put fractions together? Common denominator. So I am going to multiply this one by square root of x squared plus 2 over square root of x squared plus 2. You don't have to show that, obviously. I'm just showing it for the lesson, but kind of hard to squeeze in there. And something interesting happens when we do this. Take a look. I've got square root of x squared plus 2 times the square root of x squared plus 2. So what is that? When I multiply on the top here, this is like over 1, right?
X squared plus 2.
It's x squared plus 2. So on top, I get 2x times x squared plus 2. And that's going to be over square root of x squared plus 2. So I'm going to put it together, plus x squared plus 4. And all of that over square root of x squared plus 2. So we sort of accidentally rationalize the top, but if you look back at what why this is working out this way, that happens often.
Instead of doing this, can we just go on top and common factor x plus 2 over minus 1 over 2? Just common factor that out. On the first
Say that what would I common factor out?
on the first line.
Here?
No, up. Yeah, up there. Just x squared plus 2 over 1 over 2.
X squared plus 2 to the 1/2, like common factor that out somehow. You probably could. I think I can visualize what that would look like. But this one's a positive and this one's a negative. So for some people that's tricky, but some people that's a trick that they use. And yeah, I mean, try it. And as long as you get to the same simplified step that we get to, it would be fine. Yeah. Okay, so we're not done yet. What are we going to do now? Expand and simplify on top. Everybody happy? What do you think? Thank you very much. There's a common factor of x. That's one of the moments that would be easy to miss. And I mean, that's not the end of the world, but fully factored means fully factored. And now I think we're done. So why do you think this is something that we're going to work on? Because this is a lot harder than what we were doing before. And there's harder ones coming. Why is this helpful? Why is this something that we would want to do? Anybody have an idea?
If you want to maybe use the derivative later on in the question, then having it simplified and not having a bunch of exponents would be helpful.
Yeah, I mean, when you look at the end product of this one, the first line there compared to what it was, it turned out pretty nice, right? So there's that. Remember I talked about how sometimes we take the second derivative? Would you rather take the second derivative of that or this? Still looks nasty, but I think this would be better. You'd probably actually go back to that line instead of having a product rule, right? But this one right here wouldn't be too bad to take the derivative of. So there's that. Something we often do, I think I mentioned this yesterday, is we solve these equal to 0. There's a joke in calculus that if you're stuck, if it's a final exam and you're not sure what to do and you're like, oh, well, I'll just take the derivative and set it equal to 0 and hopefully get part marks. Because that's often what we do in calculus. So if you're going to solve, how do you solve big nasty things? They got to be in factored form. You would have to be able to solve. So if I look back at this one, that is solvable if I set it equal to 0, because I can use the zero product property all the way back from grade 10 to solve for when that thing is equal to 0. So that's another reason why this is a necessary skill, is if we're going to use it for anything, but in particular solving these equations when they're equal to 0 or taking the second derivative, something like that. All right. This one's a bit nasty. I'll tell you up front. So I think I'm going to take one step here and rewrite this like this, x plus x to the negative 2. This is like, some people look at this and like, oh, I'll use quotient rule to do that. No, 1 over x squared is not quotient rule. I mean, it'll work, but my goodness. Or if I had like x squared over 2, use the quotient rule. Like, no, that's just a coefficient of a half, right? So watch for those little moments when you're way overcomplicating things. But again, it just comes down to practice, right? So now this is power of a function, so I bring the 4 down. X plus x to the negative 2, subtract 1 from the exponent, multiply by the derivative of what's inside, which is 1 minus 2x to the negative 3, I think. Not so bad so far. The trick with one like this is, what do I have to do now to factor it? And it's not exactly pleasant or straightforward. So I'm going to put these back into fractions. And I'm going to have to start getting common denominators. Common denominator in the first bracket, I'm going to multiply x by x squared over x squared, right? To get a common denominator of x squared on the bottom. So this is going to be x cubed plus 1 over x squared, and all of that cubed. And this one I'm going to do x cubed over x cubed, so this is x cubed minus 2 all over x cubed. Stop me if you have questions. I'm going to do a couple things. I'll do them in 2 separate steps. But so I'm going to take this exponent and separate it. So it's just on the top and it's just on the bottom. Okay, so we'll take a step and do that. So this is x cubed plus 1 cubed over x squared cubed is multiplying the exponent, so that's x to the 6. And this one's just x cubed minus 2 over x cubed. What do you think now? We're actually getting close. Anybody see anything that we can do? So we don't have one fraction yet. We have to put these together, which I can do, because I could just multiply fractions straight across. What is this? It's a sum of cubes. That's right. It's a sum of cubes, so it has to be factored. And the whole thing is to the exponent of 3. So I'm going to do a couple things here. I'm going to do 4 times, I'll do it like this. So I'm going to factor that, which is x plus 1 times x squared minus x plus 1. Oh, yep, no, I'm good. On all of that cubed times x cubed minus 2. And all of that over x to the 6 times x to the 3, which is x to the 9th. And now I just have one step left here. You would usually write it like this. Yikes, that one's nasty. Any questions? Double check. Is there anything else in there that can be factored? That looks like a difference of cubes, but 2 is not a perfect cube, so that, no, we're not going to touch that one. I think everything else is done. Do you want me to show you the easier way of doing this one? Just kidding. It's not easier. That's a joke. It's not easier. There is a different way though, and I'm just going to get it started. And now I'm going to let you try to finish it. Which one's easier? Like some of you probably will have an opinion, and you'll probably be like, that jerk Belair, why didn't he show us the easier way to start? But I don't think it's about easier. I just think different people are different. So I could have gotten a common denominator to start. So that would be multiplying by x squared over x squared. So I would get x cubed plus 1, similar to what we did below, over x squared all to the 4th. And then probably what you would do here, instead of using power of a function rule, is do the top will be power of a function, but do the bottom like this. And then use quotient rule. So I'm going to do just a couple of steps here. Derivative of, you can write this down if you want, or try it yourself later. X cubed plus 1 to the 3rd times 3x squared. That's the derivative of what's inside times the bottom. Yeah, I'll put in brackets. Minus the derivative of the bottom times top. All over the bottom squared. So this is 12 x squared x to the 8. I think that's 12x to the 10. X cubed plus 1 all cubed minus 8x to the 7th. X cubed plus 1 all to the 4th. All over x to the 16, and I'll let you take it from there. You would be factoring the top, just like the first example that we did, and working things out. And believe it or not, you can make it look exactly like the other part, the other way we did it eventually. But it's several more steps. It's like 1, 2, 3, 4, I don't know, 4 or 5 more steps from there still. So like, still a lot of work. But you may have a preference, and this is what it boils down to when you're practicing, getting used to how you like to do it, which way you like to approach these things. Any questions? I think we got one more. All right, let's do it. I'm going to let you get this one started, see how far you can get. Maybe you can do the whole thing. I'll give you a tip. I don't think there's any cleaning up to do. I think you can just dive right in. It's obviously quotient law. It's obviously, whoops, well, where did everything go? It's obviously power of a function on top and bottom. So there's a lot of work to do. Can you imagine somebody saying to themselves, like, yeah, okay, I can follow this. I think I'm ready. I think I can figure it out on the quiz. I don't need to practice. Like, oh my gosh, you're crazy if you don't think you need to practice this. Crazy. You're never gonna figure this out as you go and get a test done in an hour if you haven't practiced at least a little bit. How many people made a mistake right there on the first part and missed the negative in front of the 2? Because this is 1 minus x squared, so it should be negative 2x. I bet half or more of us Missed that. Watch for that. It's such an easy mistake to make. So you try to do this. Don't copy me. You try to do it, but you can check your work as you go and follow along. And this is what I'm talking about. Like I would recommend you do that once you're comfortable. As I wouldn't even show the 4 and the negative 2x separately. I would put them together. Start trying to do that because these things are long enough that if you can save yourself rewriting any step, because I'm basically going to have to rewrite this and just put those monomials together. So if you could do that in your first step, that'd be good. Like 3 times 2, come on. You know you're going to take the derivative of what's inside. I brought the exponent of 3 out front. The derivative of what's inside is 2, so you just turn into a 6. Don't you think? But anyway. And don't forget to square the bottom, so it should all be over 2x plus 6 to the 6. Now we're going to common factor on top. Hopefully you've already started doing that. I'm going to pull out a negative 2 because I think it just kind of makes things look nicer in this case. So take a look up here, see what I have. You can do it now or you can do it in the next step. I've got 6 of these on the bottom, but I've got 2 of them up there, and that's like out front. That's kind of factored out to the front. So can't I do this? Change that to a 4. Simplify it a little bit. So this looks like it should be 5x squared plus 24x plus 3 all over 2x plus 6 to the 4th power. And what do you think? Happy with that? Not a difference of cubes, but it's actually a difference of squares, but it's cubed. So it's, yeah, very good. Notice the difference of cubes. What else? That could be factorable. B squared minus 4ac. Turns out it's not, I believe. Check it though, and always check it. It would be a bit of a fluke. I can't even imagine what would go into designing a question where you took the derivative and you ended up with a trinomial here that's factorable, but it could happen just by accident. So you got to check it. B squared minus 4ac. And so this is 1 plus x and 1 minus x all cubed times 5x squared plus 24x plus 3. And like we did last time, I'm going to have to rewrite that as separate brackets. Now what do you think? There's a common factor in the denominator. Anybody see that? 2 and a 6? I think there's a common factor in there. And this is a bit messy because it's a common factor inside the 4. So this would actually be like 2 to the 4th times, what was it, x plus 3 to the 4th. Is that right? X plus 3. And so, and this 2 will also cancel with one of those. So whether you think of that as a 16 and then cancel, or do it here with, whoops, I should do that again. Make it a 3 is up to you. So this is 8x plus 3 to the 4. And I think that's actually done.